So hello everyone, my name is Mohammed Shah and my fellow group members are Parminder Singh and Tina Basi, and we are the group The Landers. And this presentation will be for our course MECH 3302. So when we were first given this project, we were given a set of few options to choose from as far as the mechanisms are involved. So we were given a vehicle spoiler, we were given a convertible top mechanism, a prosthetic knee joint, a window opener mechanism, a kinematic sculpture, wing flaps, and finally an aircraft landing gear. So we as a group, we decided to go with an aircraft landing gear. So where's the project objective? Well, it was basically to design and analyze a landing gear on SolidWorks. So basically what we had to do is to create a CAD model and really understand the mechanisms that are embedded in a landing gear, and also to understand how it works. So the problem statement that we have, and as you can see from our quick little video here, we can see that landing gears are one of the most essential components of an aircraft. Even though we have our wings and our fuselage, landing gears really ensure safety not just for the aircraft, but also for the passengers that are in the plane. So it's really an important part of an aircraft. So just a quick background of our landing gears, which are basically located in the undercarriage of an aircraft. It usually includes wheels that it usually rests on while it's not in the air. They're essentially vital because it ensures safety for the passengers, and it is really important to design a proper mechanism of a landing gear because it allows it to absorb and dissipate high amounts of kinetic energy while it's taking off and landing to really support the aircraft but also support the passengers inside. So this is just a basic layout of what a landing gear should look like. So we have our actuator here, then you have your brace, then we have our shock strut, which is the basic cylinder, we have our torque arm, our lever, and our piston, and of course we have our tires. And here we have our CAD model that we designed. So right here we have our actuator, we have our brace, we have our piston, we have our torque arm, and our lever. And this is the main, which is our shock strut. And this is of course the tire. So before we just go delve into our calculations, we just want to quickly show a layout of our landing gear, what our CAD model looks like. So for calculations, we basically decided to do two main calculations, which is finding the mobility of our design and the crash-off value. So to find the mobility, we have to use this equation right here, which is basically m equals to 3 times n, which is number of links, minus j, which is number of joints, minus 1, and plus the summation of the degree of freedoms of relative joints, which is basically the degree of freedom of all the joints that are in our mechanisms. And when we look at the crash-off value, you have our S, which is the shortest link, we have L, which is length of the longest link, and our P and Q are the length of the remaining 2 links that we have. So before we do our calculations, I just want to show the givens that we have in our mechanisms. So when we look at link A, which is right here, which is supposed to be 50 centimeters, and our brace, which is right here, is supposed to be 20 centimeters. Our torque arm, which is right here, is 15 centimeters, and our distance OD, which is basically from here to here, which is our shock strut, that's supposed to be 53 centimeters. And the distance from O to A, which is basically the whole thing, supposed to be 66 centimeters. The diameter of the tires are supposed to be 30 centimeters. And now when we count the number of links that we have in our mechanisms, it comes up to be 9. The number of joints that we have comes up to 11. and the degree of freedoms of relative joints comes to 11 as well, since we don't have any sliders or any kinds of joints or mechanisms that result in degree of freedom of 2. So now that we have our givens all stated, now we can just go and plug into our formulas. So for the mobility we have this formula. So now we just plug in our n, our j, our f, and the mobility that we get is 2. And what this means is that in order to complete a full revolution of the mechanisms, we would need at least 2 motors. And as when we look at the Grashof, you have our shortest link, which is 20 centimeters, our longest link is 64 centimeters, and the remaining 2 are 50 centimeters and 33 centimeters. And when you plug in into the Grashof equation, we notice that it does not satisfy the Grashof requirement, which means that this link is a non-Grashof type. Now we're going to look at the trajectory of our landing gear. So position 1, which is basically its starting position, and as it starts to expand, as you can see in position 2, it starts to follow a path as it starts to expand to its final position. And position 3 is the final position when it completes the full revolution and reaches to its final position. Now we're just going to quickly look at an animation of our trajectory. So I'm just going to see it one more time. And there's our presentation. Thank you for watching.